Huawei is not allowed to buy the machine that prints modern chips. One company on Earth makes it, $200 million each. So Huawei stopped trying to make transistors smaller. It folded the chip instead. 238 million transistors in 1 square millimeter. That is early 3 nanometer territory on machines that should never get there. Huawei says the chip ships this autumn, in a phone. And the part nobody wants to talk about is the heat. Start with the machine at the center of all of this, because everything else is a reaction to it. An extreme ultraviolet lithography machine is the most complicated object humans build on a production line. Here is how it actually makes light. A droplet of molten tin falls. A laser hits it twice. The tin becomes plasma. The plasma throws off ultraviolet light. It does that 50,000 times a second. The light is so short wavelength that air absorbs it, so the whole machine runs in vacuum and bounces the beam off mirrors polished flat to the atom. Every one of these machines is built in one town in the Netherlands. Not the best supplier, the only one. And since 2019, the Dutch government has refused to license a single one for export to China. So Huawei and SMIC did what cornered engineers do. They abused the older machines. The trick is called multi-patterning. Print, etch, shift, print again. Instead of printing one impossibly fine pattern in a single pass, you print a coarse one, cut it, offset it, and print over it again. Line by line, you build a structure finer than the machine was ever designed to draw. It works. That is how SMIC reached 7 nanometer class chips with equipment nobody thought could get there. It also multiplies the steps, the cost, and every single chance to ruin a wafer that already took months to build. And it has a ceiling. This year, they hit it, which is where the story turns, on a number most people have never heard. By Huawei's own figure, more than 80% of the energy in a modern chip is not spent computing anything. It is spent moving data from one part of the chip to another. The computer is not thinking, it is commuting. Picture the chip as a city. More than 20 stacked layers of metal roads, all of them flat, all of them running sideways. And every road charges a toll. Resistance slows the signal down. Capacitance acts like a tiny battery that has to be charged every time a single bit moves. Engineers call the pair RC delay. It is the quiet reason clock speeds stopped climbing years ago. A modern flagship processor holds hundreds of billions of transistors spread flat across silicon. Signals crawl sideways, centimeters at a time. 60 years of shrinking the transistor, and the bottleneck quietly moved to the distance between them. So Huawei asked a different question. What if you stop shrinking and start folding?
At this very moment, the logical folding miracle occurs.
Take a sheet of paper. 2 points at opposite corners are a hand's width apart. Fold it once and they are touching. That is the whole idea. Parts of the processor that used to sit side by side get split apart and stacked on top of each other. A journey that used to run millimeters sideways now runs a few microns straight up. Huawei calls the architecture LogicFolding, and the principle behind it, the tau scaling law. Tau is the symbol engineers use for a time constant. The claim is blunt. Stop optimizing space, optimize time. It was announced on the 25th of May at a circuits conference in Shanghai by He Tingbo, the engineer who runs Huawei's chip division.
In 2026, logical folding take it all the way to 238 million transistors per square millimeter in one single step. And
238 million transistors per square millimeter, a 53.5% jump over the flat version of the same design. For reference, that is roughly what an early 3 nanometer process delivers. And Huawei got there without ever touching an EUV machine. And this is not a conference paper about the future. Huawei says it is the Kirin chip going into phones this autumn. Their own wording is careful and worth reading exactly as written. Now the part that decides whether any of this survives, contact with a factory. Stack 2 layers of logic on top of each other, and they have to talk to each other billions of times every second. You connect them with millions of copper-to-copper links. It is called hybrid bonding, and the tighter you pack those links, the more data can cross between floors. The best in shipping silicon today sits around 9 microns apart. AMD's stacked cache is roughly there. Intel and TSMC are in the same neighborhood. Huawei's roadmap needs 1.5, 6 times tighter than anything in mass production. New tools, new chemistry, new ways to test connections you can no longer see, and then physics turns up, and physics does not negotiate. We already stack chips. High bandwidth memory stacks 12 dies on top of each other, and it works fine, because memory is mostly sitting still. Logic is not sitting still. Logic switches billions of times a second, and every switch turns into heat. Fold the logic, and you concentrate more performance into less volume. Performance goes up. So does temperature, in exactly the place you can no longer reach. A data center answers that with liquid cooling, cold plates, and a heat sink the size of a brick. Huawei's first target is a phone. Thin, sealed, glass on both sides, sitting in your hand. There is nowhere for that heat to go. A chip that cannot shed heat cannot hold its speed. It just quietly slows down until nobody notices the breakthrough anymore. So how much of this is actually new? The bonding target is a genuine breakthrough if they land it. The rest is a direction the whole industry was already walking. AMD stacks cache on top of the processor. Memory has been stacked for years, and research labs are already stacking the transistors themselves. And the headline number deserves a careful reading, because 2 stacked mature layers are still 2 mature layers. Huawei never actually claims a 1.4 nanometer process. It claims a density equivalent to 1 by 2031, achieved through architecture rather than lithography. That distinction matters. Moore's law gave you more transistors for less money. This gives you more performance for more packaging, and packaging is not cheap. It is a real strategy. It is just a more expensive one, chosen by a company that was left no cheaper option. Which is the part of this story people keep missing. The export ban did not stop the chip. It changed what the chip is. A country locked out of the world's only chip printer decided to stop printing finer and start building upward. Whether it holds comes down to 2 numbers, 1.5 microns, and how many degrees a phone in your pocket can take. The first answer arrives this autumn in somebody's pocket.